Hi, everyone. Like Andy just said, my name's Jordan, and I work at Microsoft's Offensive Security Research Team. Today, I'm going to be talking to you about exploiting Hyper-V. And you might be wondering, okay, you work at Microsoft, why are you talking about this? What's the point? And so it turns out this team that I work on, Microsoft OSR, you probably have not heard of, but we are continuously writing exploits for Microsoft products. And the whole idea behind that is that we are hoping that by developing these exploits ourselves, we will be able to get ahead of attackers and try to figure out not only where vulnerabilities are, but also what kind of exploit techniques will be necessary to exploit these vulnerabilities, right? And if we are able to do that, then we can come up with mitigation strategies, mitigation technology that we can implement in Windows before these attack techniques are actually used in the wild. And so Hyper-V is a target that we had last year. And I feel like it's a pretty good example of our work in terms of diving deep into a component, finding some vulnerabilities, exploiting those vulnerabilities, and then using our learnings from this whole operation and applying them to Windows in order to harden it. And so that's basically, I just basically laid out the entire talk for you. We're going to be looking at vulnerabilities in Hyper-V. We're going to be exploiting them, and then we are going to be talking about how we can make Windows better and harder to exploit in this context. In addition to that, there will be a live demo towards the end of the talk, so please don't leave. The live demo will be pretty cool. And yeah, let's get going. So the first thing is, if we want to talk about Hyper-V, we need to actually understand what Hyper-V is. And I don't expect any of you in the audience to be intimately familiar with the, all the details of how Hyper-V works. So I'm going to start very, very high level. Essentially, this is Hyper-V, right? If you were to use Hyper-V on your desktop machine, this is what you would see. You have your own little desktop up there, and you have a little window, and in that little window, you have your own little other desktop, right? And so what's going on here is you have the host operating system, which is hosting these virtual machines. And in that window, you have the guest operating system, which is running inside of one of those virtual machines. And so what Hyper-V is it's the virtualization stack that makes it possible for that guest operating system to run. If you want to look at it from a slightly more detailed point of view, this is what you would get. To the left, you have the host operating system, once again. To the right, you have the guest operating system. And what you can see is that the host operating system is able to talk to hardware directly, for the most part, and the guest operating system is not. Both of them are able to talk to this thing called the hypervisor, which is kind of a blob in there. It's a level of security superior to the kernel. It has its own memory. Even the host operating system is not meant to be able to mess with that. And so the hypervisor is able to talk to hardware. The host operating system is able to talk to hardware, but the guest OS is not. And you might be wondering, okay, well, that's cool, that makes sense, except it doesn't, because what if a program in my guest OS wants to access network? What if it wants to access the storage? It has to be able to do that somehow. And so let's take an example of this process, foo.exe, which is running in user mode in the guest OS. So foo.exe wants to access a file off a hard disk, right? It's going to do that by using some system calls to talk to the guest operating system. The guest OS typically would just go and talk directly to the hard drive. Unfortunately, like I just mentioned a couple times, the guest OS does not have access to hardware. So what happens instead is the IO stack in the kernel guest OS is going to talk to this driver that lives in the guest OS kernel that's called store VSC. So VSC in this context stands for Virtualization Service Client or Consumer, or one of those two. And basically the idea is that this store VSC is going to kind of provide an interface that looks like a hard drive and is instead going to talk to this big blob in the middle called the M-bus. And the M-bus you can think of as a communication channel between the guest and the host. Right? And so then on the other end of the M-bus, of course, in the host, you're going to have the equivalent to store VSC that lives in the host, store VSP. And so in this case, VSP is Virtualization Service Provider. And basically, that's just going to decode whatever it is that store VSC is asking for, and then do that operation on the guest kernel. It's going to go through its own IO stack, and then it's going to jump into the hardware. So it's going to talk to the hard disk, get the sectors that the guest OS might be asking for, and that's just going to be that. which is cool. If you think about this like a sandbox model, you can really think about the host OS as being, being a broker, right? It has the ability to intercept every I/O access, essentially, that the guest OS is going to have, and so it can decide, okay, I want you to be able to access this piece of hardware, I want you to be able to access this piece of hardware, but not necessarily like this other piece of hardware, right? And in the middle of that, of course, the guest OS does not have access to all of memory. It only has access to a few CPU cores, which is decided by the hypervisor. And so, yeah, we have like a very tight grip on what the guest OS has access to or not. Now the thing is, I just talked about VMBus as like this kind of blob communications channel between the host and the guest. Didn't really explain how it works, and that's kind of important. The thing is, you might be thinking, okay, if you looked at that last slide, we actually have the guest OS and the host OS have access to the hypervisor, right? So we might as well just use the hypervisor as that communications channel. Of course, you don't really want to do that because context switches into the hypervisor all the time are kind of expensive. So instead, what you're going to do is use this concept of shared memory between the guest and the host. And basically what's going to be happening there is you're just going to pick a piece of memory in physical memory, and you're going to be able to map it in both the host's memory space and the guest memory space. Once that happens, you can kind of have VMBus interpret that piece of memory as a ring buffer, which means that you're just going to copy a packet into it, and another packet, and another packet, and then when you run out of space, you just start over. And so based on that, transferring data to and from the host is pretty simple. You just have this packet in your VSC, you copy it into the ring buffer. Since that piece of memory is shared, the packet just like magically shows up everywhere this piece of memory is mapped at, and then the host will be alerted that there's a packet in there, it's going to grab it, interpret it, do whatever it wants with it, and then that'll be that. The only problem with that is, of course, since we have the ring buffer, and these machines are highly, modern machines have a lot of threads, a lot of different components might want to be able to talk to the host OS, and using a ring buffer for that is kind of problematic if you're going to be locking the ring buffer constantly in order to talk to the host OS side of things. You are not going to be able to send a lot of packets, at least not a lot of packets that are really big, because if you're going to be constantly copying memory in and out of the ring buffer, well, that takes time. Everything is serialized because it's ring buffer, and that's not ideal. So in order to deal with that problem, we introduced this concept of shared memory that can be sent from the guest to the host through VMBus. And so you have this kind of thing there, the GPADL, I call it a GPADL, that stands for Guest Physical Address Descriptor List. If you're familiar with Windows kernel lingo, this is basically an MDL that can span the boundary between the host and the guest. So the idea is that the guest is going to allocate this piece of memory, is going to say, okay, I want to send that piece of memory over to the host, and instead of copying that memory in and out of the ring buffer, is just going to basically give a reference to that piece of memory. And then that piece of memory is going to be mapped into the host OS, and the host OS at that point can do whatever it wants with it. It can copy memory out of it, it can copy memory into it, it can keep it mapped or unmap it or whatever. And that's basically the way you're going to be able to send larger amounts of data at a higher frequency than you would be able to with just a ring buffer. So at this point, you are essentially Hyper-V experts, at least as far as I'm concerned, because I'm not a Hyper-V expert. This is basically all I know about it. And I'm here to write exploits, right? I'm here to find vulnerabilities. And so once we have this level of context for Hyper-V, which is all you're going to need for the rest of the talk, we are going to be looking into a specific component. And this component is VMSwitch. VMSwitch is just a VSP that provides network access to the guest. There's really nothing fancy here. It's basically the same diagram I was showing you earlier, except that VMSwitch is going to be accessing the network card instead of a hard disk. Right. So the thing that you're going to notice here first is, much like Store VSP, VMSwitch lives in the host OS kernel. So that means that if we are able to find a vulnerability in VMSwitch and compromise the host through VMSwitch, then we'll have full control over the host OS. We won't have to escalate out of user mode or anything. We'll just kind of be there, we'll be done, and it'll be great. So that makes it a pretty good target. The other thing to know about VMSwitch is the way that it works is it implements this protocol, which is the Rndis Protocol, which stands for Remote Network Device Interface something. And basically that's a protocol that was introduced by Microsoft a while ago that is typically used to access network cards over USB. So really, VMSwitch you can kind of think of as a USB network card that is exposed over VMBus. I'm really simplifying things, but that's basically how it works. And so thinking about how to interact with VMSwitch, you're going to have two types of messages, right? You're going to have the messages that you send to VMSwitch to kind of set up VMSwitch, tell it, okay, this is the protocol version I want to use, these are the buffers I want to use, this is the size of the packets I want to send, and so on. And then you're going to have the second layer of messages, which are these Rndis messages, which are going to let you interact with VMSwitch basically in the same way that you would interact with a USB network card, right? And so knowing that, it kind of makes sense to start looking at the initialization sequence of VMSwitch, right? Like I mentioned, so think of it like to the left, once again, you have the host, to the right, you have the guest. And so bringing up VMSwitch is basically just sending a sequence of a few messages. The first thing is going to be agreeing on which protocol versions to use. So you're going to have the protocol version for VMSwitch that is first sent, then the protocol version for the actual Rndis protocol that is sent. And so that's, basically that's just how it works. And then after that, you're going to be sending these receive buffers and send buffers. So the receive buffer and send buffer are basically what's going to be used. So first off, they are shared pieces of memory. They are gpaddles. So the guest OS allocates them in its own memory space, sends it over through VM bus to the host OS. The host OS maps it, and then they're going to be used to basically transfer Rndis packets. The reason to use those rather than just VM bus directly is what I was saying earlier, that well, this is exactly the kind of case that you would not want to use VM bus for all the time, because network packets are going to be large. They're going to be happening at very high frequency. So a ring buffer is really not ideal for that, especially since things can happen out of order and all that. So basically, we introduce a send buffer, which is going to be used by the guest to send packets, and the receive buffer, which is going to be used by the guest to receive packets. And that's just basically, you can think of those as alternative communications channels that VMSwitch is going to use. So in terms of looking a little more in detail at how these receive buffers and send buffers look, like how they work, right? So we said we have these messages that sets them up in the host OS. So we send them over. We send this big blob of memory for each the receive buffer and the send buffer. The thing is, we want to be able to send and receive more than one packet at a time. So what happens is the host OS is responsible for subdividing the receive buffer and the send buffer into smaller sub-allocations. The reason for that is you want to be able to send and receive more than one packet at a time, because again, networks are a nightmare and there's a lot of packets all the time, and you have to deal with that. And so the important thing here is the host OS is the one who makes that decision and sends back those bounds for sub-allocations. Next, if we have the guest wants to send an Rndis packet, in this case it's a query packet, which just means asking for things like the MAC address or something like that from the host, is going to generate its Rndis packet locally, is then going to send it into the send buffer, just copy it into the send buffer, because once again it's a piece of shared memory. And once that happens, it's going to send a message over VM bus to let the host VMSwitch know, like, hey, there's a message, there's a packet in my send buffer. Please read it. Please take care of it. Once the host sees that, it's going to copy it into its own memory space. It's then going to acknowledge to the guest that, okay, I've read it out. You can now use this send buffer for something else, like this send buffer sub-allocation for something else. Then it's going to handle it. And then it's going to copy the completion message into the receive buffer, let the guest know that there's a packet in the receive buffer sub-allocation number 2, and then the guest is going to copy that and take into account that whatever has happened, and acknowledge to the guest to the host that, okay, we're done. You can now copy more stuff into this receive buffer sub-allocation. So that's basically how it works in terms of sending and receiving the Rndis messages. What's interesting here is that we're not just using the receive buffers. We're still also sending these things over VM bus. And the thing that's kind of interesting about that is the reason to use the receive buffers and the send buffers, as far as I can tell, is to kind of have this really highly parallelized way of handling those messages. And having this level of asynchronicity, even though, but the thing is, like, VM bus by its very nature, because it's a ring buffer, everything is serialized, so it kind of doesn't entirely make sense, right? How do you marry the two? So looking more specifically at how the host OS VMSwitch handles those messages, it doesn't just handle them directly, and so we're going to take a look at that. Let's say you have the guest that has sent these two messages through the send buffer. It lets the host OS know through VM bus. The host OS receives them. And then instead of just handling them directly, it's going to copy them into a queue and then acknowledge that it has received them. Then it's going to do the same thing for the second message, put it into a queue, acknowledge that it has received that message, and that's basically it at that point. And the reason for that is that once again, all of the VMBus messages are handled in a very serialized way, and this is all in a single thread, and you don't want to be stalling that thread for however long it takes to actually handle those messages, which is why they're put in a queue, and then they are actually handled by these two separate worker threads, which you can think of as actually belonging to VMswitch. So then they're going to be used there, they're going to be copied out of the queue, they're going to actually be handled, and then the results are going to be copied they're going to be copied into the receive buffer by the actual worker thread as opposed to the VMBus thread. And I know all these details are kind of boring, but they will all come up later, so try to pay attention. And so after that, the host OS is going to acknowledge that it has finished this message. It has placed the completion message into the receive buffer. It's going to do the same thing for the other message, acknowledge it to the guests, and that's basically it. Okay, so once again, you're now complete VMswitch experts, at least as far as I know. I don't really know much more about VMswitch than that, and I'm going to try and now walk you through how I actually found the vulnerability that I did and how I exploited it and all that. So we just took a look at the VMswitch initialization sequence, sending a few packets, first negotiating the protocol version and all that so that every end knows what to talk about. But one way to kind of find vulnerabilities typically is, you have these very well-defined sequences. What if you mess with that sequence, right? What if you send one message before the other? Or what if you send one message multiple times, like do interesting things happen? Turns out interesting things do happen if you send a receive buffer multiple times. So for example, here, we're going to have the guest define gpal0, so shared memory between the guest and the host, and it's going to send first receive buffer. And it's like, okay, the host is going to map gpal0 as its receive buffer, and you have a pointer that points to it. Totally cool. After that, it's going to do a second gpaddle, and instead of sending it as a send buffer, it's going to send it as a receive buffer. And what happens here is interesting, is that the receive buffer pointer is updated, right? It now points to gpaddle1 instead of gpaddle0, even though we are not actually supposed to be able to have more than one receive buffer. In fact, there's no longer any reference to the old gpaddle0 mapping in the host OS VMswitch. It's just kind of there. It's still mapped there. And well, that doesn't seem like a huge deal, but yeah, if you keep doing it, it just keeps happening. And at that point, you may be thinking, okay, well, that's kind of weird, but at worst, it's probably just a memory leak, right? Because you keep mapping more and more memory into the host. And even then, you're really just mapping more and more physical memory. You're not really allocating new stuff into like the host pool or anything. So even if it is a memory leak, it's probably kind of tiny and insignificant. But the thing that's interesting is if you look at the way that the receive buffer is initialized, and in turn how it's updated, because it turns out we are able to send the receive buffer more than once, that operation is not atomic. And because the team did not necessarily expect the ability from an attacker to send more than one receive buffer, there is also no locking on this operation. And so if you take a look at how the buffer update works, there are 3 steps, right? Because the first step is what I was just showing in this slide before, is updating the receive buffer pointer, right? So it's pretty straightforward. The thing is, as mentioned before, the host OS is also responsible for generating sub-allocations into that receive buffer, and then sending them back to the guest OS. And so that's actually what the second step is actually generating that list of sub-allocations inside of the receive buffer. And then the third step is to actually update those sub-allocations. And so it might not seem like a huge deal, but if you take a look at how this works, let's assume that we have gpaddle0 and gpaddle1 both mapped in the host OS. And the guest OS decides, okay, let's use gpaddle0 as our receive buffer. So the host OS is like, okie dokie, here we are. We have a pointer, and now we have sub-allocations to that receive buffer. It's all good. But now the guest OS is being annoying, is telling it to use the gpaddle1 instead of gpaddle0 as a receive buffer. Well, the first step is to update the pointer to receive buffer, right? And so as that happens, first step, the pointer is going to be updated, and implicitly, the sub-allocation bounds are going to be applied to this new receive buffer. And in this specific case, because we have gpaddle1 smaller than gpaddle0, those sub-allocation bounds are actually going to go out of bounds of that receive buffer. And well, I mean, I don't really need to tell you that it's not a great thing. Of course, if you let it go, if you let it generate its new sub-allocation bounds, and you kind of like let it go all the way to step 3, it's totally fine. After that, you end up with a perfectly valid receive buffer, like a really good receive buffer, and it's totally possible to use it. Unfortunately, you do end up with like this tiny window during step 2 where you are able to potentially write data out of bounds from that receive buffer. And well, it is like a really tiny window, right? This is basically generating the sub-allocations for a receive buffer. That's really just dividing the size of the receive buffer by the number of sub-allocations and then, generating like some data structures and stuff. So it's really just probably a few hundreds of cycles. But it is a possibility, right? Because as mentioned earlier, we do have these Rndis worker threads that are running in the background, working on Rndis packets. And so if those are running while you update these sub-allocations and you can somehow make them write to the receive buffer as the sub-allocations are being generated, then you'll be able to write data out of bounds. And so that's basically the vulnerability. And now in terms of exploiting it, you really have to deal with 3 things, which are kind of annoying. The first thing is, okay, can we even control what's going to be written to this receive buffer? Because once again, this is going to be written by the Rndis worker threads, not by data that you necessarily directly control as the guest OS. So that might be tricky. Second thing is, can we even win the race? As mentioned, this is a fairly tight race. And again, you're doing this from the guest OS, but you are not the one that is directly racing the host OS. You've basically got to get the host OS to race itself. And well, I mean, that's kind of annoying. And the third thing, of course, is, okay, even if we do have the ability to hit the race and control what's being written, can we even put a useful corruption target behind the receive buffer? Because typically, at least for me, in my experience for kernel exploitation, I'm used to having an out-of-bounds write out of a pool buffer, right? I don't know where these shared buffers are mapped. This is not in the pool for sure. So got to take a look at that and try to figure out if I can do anything useful with that. And that's what we're going to get into right now. So the first thing is, can we even write useful data to the receive buffer out of bounds? The short answer is yes. It's actually not that difficult. If you take a look at how the Rndis protocol works, basically every message that you send to your network card is going to have a complete message. And some of the complete messages, such as the complete message for the Rndis query message, include a buffer at the end, a buffer that can contain arbitrary data. And so basically, the kind of data that you're going to be querying through this is going to be stuff like I mentioned earlier, for example, the network card's MAC address, right? And these are things that you might be able to set through the Rndis set message. So basically, the idea from here is you're going to find an OID that is handled by a VM switch that lets you set some data that can be returned through the query message. And I'm not going to go into detail in terms of which messages actually allow you to do that, but this is the basic idea. It's really simple. And from that, you can actually control a fair amount of data that is going to be written out of bounds. And you actually even control the length that's going to be written. And at that point, it's like, yay, we got number 1 down. Number 2 is a little trickier. How do we win that race? Well, the first thing to know is we've been talking about how these Rndis messages are being handled in parallel in the background by these worker threads, right? And so ideally what you would want is, okay, maybe you have this queue, right? Maybe I can just queue a bunch of messages and they're all going to be handled in the background, one after the other, and each one is going to be completed and going to be written to the receive buffer. Unfortunately, if you take a look at what happens if you try to do that, so here we have 2 worker threads. Practice, there's actually 5, but let's say there's only 2. You have these 2 worker threads, there's 3 messages that are queued, and what happens is the worker threads each pick up a message, it handles it, then it writes it to receive buffer, and after that you would expect it to actually grab the third message and handle it. Unfortunately, no. What happens after that is because they alert the guest that, hey, there's something to grab in the receive buffer right now, you should go and do that. It's going to actually wait for the guest to say, okay, yeah, I grabbed it from the receive buffer, and you can now use that slot in the receive buffer once again. So basically, unless the guest actually sends one of these acknowledgement messages, these worker threads are just going to be stuck. And once you do receive an acknowledgement message, it's not going to be stuck anymore. It's just going to keep handling message after message after message. The problem is, in our case, these acknowledgement messages have to be sent over the VM bus channel, which once again is completely serialized. And that's also that's also the channel that we have to send the new receive buffer over. And so basically, the receive buffer message and the acknowledgement message cannot ever be handled at the same time. So you cannot actually unlock this thread as you are trying to hit the race, which is kind of the problem. So that's one idea down. But if you think about it, the very reason that these messages are, that these worker threads are being blocked until it receives an acknowledgement from the guest is that, as mentioned, they all kind of like use a few slots of the receive buffer. And they want to make sure that whatever is in those slots has been read out before they write something else to them. But so that's a problem because every message in the Rndis protocol actually has a complete message, and so every message that you send over is going to be doing that. And it's going to be writing to the receive buffer and waiting for it. Unless you take a look at the failure paths. Fortunately, if you look at how VMswitch handles certain Rndis messages, it turns out that certain failure paths will cause it to never try to write to the receive buffer. It's just going to return an error, and it's just going to skip that message and jump to the next message in the queue. And so there's this idea then of the Cascade of Failure, which is also the title of my autobiography. Cascade of Failure being that, okay, you're just going to queue a bunch of messages that are going to fail, and that's going to create a sufficient time differential that you are able to control as an attacker such that you can try to hit the race. Because maybe we can't get messages to continuously write to the receive buffer, but all we really need is one buffer, like one message to write to the receive buffer. And the only difficulty then is like we need to be able to control when that message is going to be written to the receive buffer. But if we are able to have an arbitrary number of messages fail before that, then we'll be fine. And so trying to visualize that, you can see, you can imagine, okay, each worker thread is already handling an actual valid message. Okay, it's going to handle it. It's going to send it back to the guest, and then it's going to be blocked. Then the guest is going to send one acknowledgement over VMBus. And that's kind of what's going to start this whole cascade. You can see Rndis messages 3 through 7 each have like that little crash thingy there. That just means it's a malformed packet. And so as soon as it's going to be tried to be handled, it's going to go into there, it's going to fail, and then it's just going to go to next message, and next message, next message. And as you can tell, that took a few seconds. So in practice, that would just be like a few microseconds or nanoseconds or whatever. But the whole point is that we created this time differential. And from there, this actual last message is going to be written to the receive buffer. And so if you control that data, then we're all good. The only difficulty with that is, well, you want to win that race, but you don't actually know how long you want to wait, right? And you don't even know how long you are going to be waiting by. You only know that the amount of time, like this time differential that you're creating, is proportional to the number of messages that are going to fail. But you don't know how long like one message failure is going to take, right? And you also don't know how long you're going to want to wait. So it's kind of annoying. But maybe we are able to distinguish between the race being too early, like us being too early in the race or us being too late in the race. And if we're able to do that, then we can just adjust the number of failure messages to increase if we're too early or decrease if we're too late. And so taking a look at what happens if you're too early, well, if you're too early, you're actually just going to be writing to the old receive buffer with the correct sub-allocation bounds. And so your message ends up in here. And since the receive buffer is something that is shared between the guest and the host, well, as a guest, you can just like read from that receive buffer and see that, okay, we were too early. Let's try again. If you're too late, it's going to be the same thing, but with the new receive buffer. Because if you don't hit the race, inherently, you are going to be writing into the bounds of one of your receive buffers. And so the only difference is which receive buffer are you writing into, and you're able to distinguish those because as a guest, you are able to read from that memory. And so if you're just right though, well, you're not going to see anything in either of those receive buffers because by definition, you're writing out of bounds, which is what we want. And at that point, all you have to do is celebrate. So we are able to win the race, and we're able to write arbitrary data out of bounds. It's pretty great. The only thing is, we still have no idea where our buffer is. We have no idea where we're actually corrupting. It's kind of annoying. So, pulling up KD, doing bang address, what you're going to see is that Well, there's a bunch of other gpaddles and other MDLs are allocated into that memory region. But the other thing that is allocated in that memory region, which is really nice, is kernel thread stacks. And that is a very juicy attack target. Because really all you have to do is like overwrite one return address on there, you get ROP, and you're done. So it's kind of a blessing. The only thing is, it's also not. Because it turns out, if you have this allocator, right, and you want to somehow place one target after your buffer, you need to be able to basically massage the allocator into doing that. The difficulty is, as a guest OS, you don't really have any control over what threads are going to be created in the host OS, at least not directly. And so that means if you can't create new threads in the host OS, you can't create new stacks. If you can't create new stacks, you're going to have to try to corrupt an existing stack, and that's also difficult. So there's basically three things to deal with. It's, okay, first off, how does this allocator even work? Secondly, can we place a stack at a known address? And in order to do that, well, a known offset, in order to do that, we actually also need to be able to place a stack in the first place. So a lot of non-trivial stuff. Well, first thing is, well, actually, the allocator is kind of trivial. It's kind of nice. So the name of this region that contains these MDLs and all these stacks is a system PTE region. And the allocator for that is just a bitmap-based allocator. So what you can see to the right, it's an artistic representation of this bitmap. In orange, you're going to see bit ones, which mean that a page is allocated. And blue is going to be bit 0, which means that a page is not allocated. And the way that this allocator works is basically it has this little yellow arrow in there. That yellow arrow is called the hint, and that's basically a heuristic for where the bitmap allocator is going to start scanning into the bitmap. And so in terms of allocating something into that memory region, it's actually really simple. The allocator just scans the bitmap. If it finds a group of bits that are contiguous, that are big enough for what you want, it's just going to place that memory there. If it doesn't, it's going to add some more memory. So as an example, let's say we want to allocate 5 pages. The hint is right in the middle there. It's right before a big free region. And so it actually does already have 5 pages right available there. It's just going to allocate it and update the hint to go after that allocation such that you don't have to scan that again next time. Let's say you want to allocate 5 pages again. Well, you don't have 5 pages immediately available, so that little arrow is just going to scan the bitmap and find 5 pages here, allocated there, and then you are going to be done. Now, let's say you want to allocate 17 pages. Well, you actually don't really have any free memory in there that has 17 contiguous pages. So instead, it's going to expand the bitmap. It does that in groups of 2 megabytes, and then place those 17 pages there, and that's that. The annoying thing if you end up doing that is that the hint is not actually updated, which can come in handy or can become annoying based on what you're trying to do. Just something to know. Now, okay, so we understand how the allocator works. It's actually pretty simple, but we need to be able to interact with that allocator in a meaningful way. We need 2 things. We need to actually be able to ideally allocate arbitrary amounts of data arbitrary times. And that's actually really easy because we have this vulnerability where we are able to map receive buffers and send buffers over and over and over again. And since these are gpaddles, and gpaddle size is controlled by the attacker because it's controlled by the guest OS, you can basically allocate any piece of memory of any size, which is a really nice primitive. The next thing is we need to be able to allocate new kernel thread stacks such that we can place them after our receive buffer. And that's actually really annoying. As I mentioned, there's like really no good way, like there's obviously no by design way to do that from a guest. And so the best way that I found how to do that is to notice that VM switch and a lot of VM bus based services actually rely on the NT system worker thread pool. The reasoning being that once again, VM bus messages are all serialized. You'd rather be doing that in parallel. So basically it'll read a message, submit a task to the worker pool, then the worker pool is going to take on that task, handle it, and in the meantime, like the VM bus thread can like go on to handling another VM bus message. But so the way that a thread pool works is whenever it gets a task, if there's a free thread inside that pool, it's just going to use that thread, right? And so no new thread is created, no new stack, which is not great for us. But if all the other threads are already busy, it's going to actually create a new thread, add it to the pool, and that's going to create a new stack. So the idea is basically just kind of find a message that is easy enough to hit and we'll submit a task to that pool and just kind of flood it, just send a bunch of them. And the host OS is going to be submitting all of those to the NT kernel worker thread pool. And eventually, well, it'll create some new messages, some new threads. And that's still going to create some new stacks. And ideally, it'll place it where we want. I was also helped by the fact that VMswitch at the time had a tiny bug which would cause certain worker threads to be deadlocked, and it would just like wait on a mutex forever, which was kind of annoying, but also actually came in really handy because that way you can just make sure that like any arbitrary number of worker threads that you want is just going to stay busy forever, and that lets you allocate new ones. And so at this point, it's like, okay, we basically have a really hacky way of creating new kernel thread stacks. Ideally, we really only want to be able, we really only want to have to like spawn a single one, and so that's where we have to go into how to massage the heap, like the kernel, the system PT region, and basically just have like these 5 steps that kind of just work. The idea being of like, first we want to spray 1 megabyte blocks. And we do that in order to kind of fill in these gaps to make sure that our later allocations will not be going all the way up in there. So we do that by spraying a bunch of receive buffers or send buffers or whatever. It's pretty simple. And the next thing is we want to allocate a buffer that is equal to, in length, to 2 megabytes minus 1 page. And the reason for that is if this is the maximum size that we can allocate, that it will create a new region, like a new 2 megabyte region expansion at the bottom of the bitmap without actually like putting it somewhere else. And the reason that it's interesting is that this is actually going to be our receive buffer. If you'll recall, we need to actually hit the race several times before we are actually able to hit the right number of failure messages. And so you want to be able to place your buffer in a location where you know that the next time you have an allocation, it will end up in the same location. Because we want to be able to repeat that race over and over and over again. And so making it the biggest size possible allows us to do that. And then you just allocate a 1 megabyte buffer that's just basically to take care of possible alignment issues. I'm not going to get into that, but there's something in the appendix for that. And after that, you're going to allocate something that is 1 megabyte minus the size of the kernel stack. And then that's going to update the hint. And because the hint is right before that thing there, you can just allocate a new stack. It's going to be there. And you end up being able to place a kernel stack not an arbitrary offset from the receive buffer, but a known offset. That's really all you want. Because at this point, then we can manufacture our receive buffers in such a way that we know that the suballocation that we care about will be placed to overlap with that kernel stack. So we're good. At this point, we have filled in all 3 of those requirements, and we are actually able to write memory out of bounds, and everything's awesome. The only thing is, since we were corrupting kernel thread stack, we actually need to bypass KSLR. As you probably, hopefully know, in the host OS, all memory is kind of randomized. So we don't really know, we want to overwrite a thread stack. The reason we want to overwrite the thread stack is to overwrite a return address. We can't overwrite a return address unless we know what to overwrite it with. So we need to know the location of some code in the host OS in order to do that. And so that's what bypassing KSLR means, is just finding the address of a piece of code that is known. And the first way to do that is actually just to find an info leak. And so the info leak that I found for this exploit is actually really quite simple. Basically, this is how these this is the structure that is used by both the host OS and the guest OS for VMswitch messages. And you have this union, right? The thing about unions is not every member of the union has to be the same length. And so, for example, you have like one message to the left here that has one more field than the one to the right, and that's totally fine, except that, once you do size of that struct, it's going to be used at the same size everywhere. And that means that if you allocate that structure on the stack, never fully initialize it, and just send over like the entire size of that structure, well, you return a bunch of uninitialized stack bytes. And uninitialized stack bytes are pretty great for us because they typically contain return addresses. And so we're able to get a return address from VMswitch, which is awesome. And with that return address, we are able to build a ROP chain and get code execution and all that fun stuff. And so we're done. Except we're not. As it turns out, the info leak is awesome, but it only worked on older versions of Windows. At the time, that was Windows Server 2012 R2. So we were actually targeting Windows 10, so oops, let's find something else. And actually that new method, that other method that we're going to talk about, does not include a new vulnerability. It's just a way of dealing with KSLR without finding a new bug. And the thing to know about KSLR on Windows, at least for drivers, is that each driver is going to be aligned to this 0x10,000 byte boundary. So what that means is that if you overwrite the lower 2 bytes of an address within that module, well, you can change the offset within the module without having any information about where the module is. And so if you'll recall, we have the ability to write arbitrary data at semi-controlled offset inside of the host, inside of like that kernel thread stack. So that means that we can totally just overwrite the lower 2 bytes of something. So we can see as the example down there is we have this actual valid return address on the stack, and instead we overwrite the lower 2 bytes, and then it's going to point towards a ROP gadget. In this case, just pop R15 ret, which is not really useful. And that's kind of the thing though, it's like, okay, we can jump to a ROP gadget, cool. But we only have like 0x10 bytes, which is like 64K of range or something. And well, we can't really do anything useful with just one ROP gadget. Or can we? Thinking about the allocations again, right? We had this thread stack right after our receive buffer. And we still have the ability to map more shared memory. So what if we allocated like say a send buffer right after the thread stack? And we have this shared memory between the guest and the host right after the thread stack. And then we have the ability to jump to one ROP gadget. Well, this ROP gadget is pretty great because it's just going to do RSP plus equals like almost a whole page worth of data. And so thinking about it, you have like the thread stack at the top here on the right. You have this, this return address there. You overwrite it to jump to that ROP gadget, okay? And then what's going to happen? RSP is going to go from your kernel thread stack right into shared memory. It's like, okay, this is cool. We can like control more data that's going to be interpreted as being the stack. That's nice. But of course, once you hit ret, well, it's just going to crash because the guest OS doesn't really have any way of knowing what to put in there. That's the whole point. We're trying to get an ASLR bypass. But what's cool about that is it's going to crash. And when an x86 CPU crashes, at least on Windows, it's going to put the return address of where the crash happened onto the stack, which means that as a guest who has access to that shared memory, I can actually read back that return address of where the crash happened. And then the exception handler of Windows is going to be using my shared memory as a stack for the exception handling. And so as an attacker, I can both read and write from that, and I can redirect execution from the exception handler into anywhere I want. And so that's how you bypass KSLR without info leak. You basically just move the stack into shared memory. Doesn't work for many things, but in this case, it came in pretty handy. So as a result, we have ROP and by extension code execution on Windows 10 from a guest VM, which is cool, but let's see how that works in practice. I'm going to do a live demo. Okay, I can't see shit. Just a second. Just making sure I can actually see the screen. Okay. Okay, so this is running Windows Server 2012 R2. This is running on this little laptop here, which is not a server, but whatever. And this is a VM here, right? So what I'm going to do is I'm going to pop up my super elite hacker shell. And I first want to grab the VM bus channel that is being used by VM switch. Okay, so let's just return the address of that in the guest OS. Then I want to check that my info leak actually works. Swear to God. Okay, that just hung. It didn't crash or anything. It's just hanging there. Okay, I guess no live demo. Okay, I'm gonna keep going and try to get that working as possible. But this was supposed to work. It's supposed to be really cool. So let's keep going. In the meantime, what's happening? What's happening is what we want to do is, okay, so we have this exploit, which as you just saw, works super well, super reliable, is really awesome. And based on that, we have like this whole host of data we just got, right? And so the data that we get from like writing these exploits it's a couple things. It's first like the vulnerability discovery, right? It's a little process. Now we are able to know, okay, where to look for more for more vulnerabilities. How do we want to do that? The best way for us to do that really for vulnerabilities is either going to be introducing mitigations that we believe are actually going to kill certain types of vulnerabilities, but that's typically difficult. And instead, what we want to do most likely is going to be stuff like a lot of code review internally, or introducing a bug bounty that pays out $250,000 for working exploit. The next thing we can do is learn from our exploit techniques that we use, and hopefully introduce some new. I'm sorry, I'm trying to do two things at once. It's really difficult. Yeah, so introduce some new mitigations that will break these exploit techniques. And so, so we kind of did that in addition to like kind of trying to break the whole post-exploitation game, right? In terms of breaking the post-exploitation game, it's not necessarily going to be introducing more mitigations, although that's definitely a part of it. It's going to be re-architecting things in such a way that we make the targets less interesting. And so, in terms of mitigations that we introduce, the first and most obvious thing, I think, is just going to be separating the kernel stacks from the rest of memory. The reasoning behind that is that this way you will never be able to overflow from any buffer into a kernel stack. And so that's just better not only for Hyper-V, which has all these, has all these buffers that are handling, that are working in that same memory region, but also for other drivers that use MDLs and map physical memory and all that. And so that's the first mitigation. The second thing that we can look into is much more general mitigations, things like HVCI, so hypervisor enforced code integrity, which makes it such that attackers cannot inject new unsigned code into the hostOS kernel. In addition to that, we have things like KCFG, which is preventing the takeover of certain function pointers. And things like that in the hostOS kernel. And so that's just like very general hardening that we are definitely doing. And like these features have existed for a little while, but now there's like more and more effort to make it happen by default on more platforms. In addition to that, we are actually investing with Intel and other partners in security features that are actually implemented in the hardware. The main one of those that would actually totally apply to this exploit is CET, which is going to be a hardware implemented shadow stack, which is going to make it such that you cannot just overwrite a return address with whatever you want. And that prevents ROP, and that prevents this exploit in addition to other stuff. In terms of more architectural changes that would change the post-exploitation game, you've got, okay, this worked. We are going to switch back to this demo as soon as I can connect back in there. But yeah, so the thing I was saying is you actually have certain VSPs that live in the hostOS user mode. And the reason that that's interesting is that hostOS user mode is going to be isolated on a per VM basis. So if you break into a VM worker process, well, you've only really broken into one VM's worker process. Unlike this, where you're going to see, you actually are able to do a lot of things. So hopefully, so this actually shows that the exploit actually worked. And I'm just going to skip a few things. Let's see. First, so this is actually listing the processes in the hostOS from the guestOS, right? So you have a list of this, and well, I mean, you don't really have like any reason to believe that any of this is legitimate, because anyone can come up with a list of PIDs. But let's see if we can inject a DLL into the hostOS Explorer.exe. Yes, we can. I was like, okay, this is cool. That actually worked for once. Well, not for once. But so the thing was, in addition to that, I'm also running a second VM on this machine because I want my demos to be really complicated. And what we're gonna do is we're just gonna like kind of log into that VM, no particular reason. And from the original guest, not kist, can actually list what other partitions are living in there. Okay, so you have 2 and 3. I'm gonna guess that we're 2, because sure. And then we can actually grab the other guest. Okay, it's going to kind of hook into the other VM. And at this point, we are actually able to, come on. Okay, yeah. So there were a few more things for the demo, but you know, first failure kind of breaks things. Anyway, I have about 3 seconds left. So the whole point is like, yeah, you have one VM worker process per VM. And so if you break into that VM worker process in one of those VSPs that is in the worker process, well, you've only really broken into that worker process. If you want to have full access to all the other VMs, like I just showed you, you still need to escalate to like kernel level. And so this is something that we're definitely trying to invest in terms of, well, we are actually hardening also the worker process even more so than the kernel. You know, improvements to sandbox, improvements to RC mitigations. In addition to that, you know, we are trying to move more and more Hyper-V components into user mode because it's just a much better security posture. And okay, now my slides have, okay. And the last thing I want to talk about is just the Hyper-V bounty. So what I just demoed here, assuming it had worked the first time, is worth $250,000 to Microsoft. And keep in mind, this is about a month's work of work. So if you want to make, you know, 1, 2, or 3 years worth of salary in a month, please submit to our bounty. Pay really well. And there's actually more and more resources out there in terms of getting started. One good resource to like get started is actually a talk that was yesterday by Joe Bialik and Nico. So the slides should be available online. In addition to that, we actually have a lot of really well-documented guest-side driver code that is on GitHub. So you can just like click on that and figure out how these VSPs work just by looking at VSC source code. Really well-documented, honestly, maybe better documented than some internal code. And in addition to that, we have been publishing a bunch of Hyper-V symbols. So a lot for you to get started with, and hopefully we'll hear from you on the bounty. Thank you for your time.